His question, kind of in a nutshell, is what are some of the key observations? I suppose both astronomical observations, and he can address the more particle accelerator sort of observations that might tell us about the non-standard model that he also mentioned earlier. Basically, this sort of grand unified theory sorts of ideas of unifying all the forces of nature into one theory. From the astronomical side, astronomers have kind of done their part. Things like the observations of the cosmic microwave background radiation give us clues to the amount of something called dark matter in the universe, which is providing all sorts of problems for people to work on to figure out what the dark matter is. We don't know yet. So microwaves observations have been key in that.
Mark, do you have anything to add?
Yeah, I could add a few things to that. I think when it comes to dark energy, which Tom mentioned, one of the key projects to understand dark energy at the minute is actually looking for type 1a supernovae. They're a very specific type of supernovae. We know how bright it is. We know how bright they should be, and we can measure how bright they appear, so we can measure the distance to them. And they go off in galaxies at very large distances from us, and we can determine whether the expansion rate of the universe is speeding up or slowing down. Well, that was done about 10 years ago originally, and they said, look, the expansion rate is speeding up, and that's what led to dark energy. But they're still pursuing this project because now they actually want to get more of a handle on how fast this acceleration is, because that might actually point them in some kind of direction to explain what dark energy is. One possibility is that it's just a constant that Einstein added into his equation of general relativity, the cosmological constant. But that's just one possibility. I think also another big project that's being developed at the minute is the Large Synoptic Survey Telescope, which is going to go in Chile. It's a US telescope, but they'll put it in Chile. And it can map the sky so quickly that it's going to be able to answer a lot of questions about dark matter. And it'll also be able to look for... basically, come into the idea of warp in space, is that on a very small scale, where there are small-scale warps, the light gets distorted by these warps, but it only gets distorted by very small amounts. We call it microlensing. And the Large Synoptic Survey Telescope will actually be able to look for this microlensing, and from that also you can get a handle on what the nature of dark energy is. So there's a couple of projects that I think might be able to answer some of the questions that Tom was asking.
Damon?
Well, let's see. I guess my colleagues here have handled the big end of things, so I'll deal with the small end. I guess probably the biggest thing is probably what's going to happen with the Large Hadron Collider over in CERN. They're actually probably going to be the first group of people who directly observe some potential explanations for things like the dark matter, for these things that might explain what's going on with the standard model, to help us revise our understanding of cosmology and how the universe is put together. So the LHC, what they're doing there with the Large Hadron Collider is actually trying to collide things with enough energy that they create some of these new particles out of that collision. So they're very huge machines. They collide things with great energy, and they're hoping to observe things like what's called the Higgs-Boson, which is a fancy name for basically the idea that that's what gives everything mass. That's something we don't really have a handle on yet, is why do things have mass? The standard model predicts that this particle, the Higgs-Boson, is the thing that does it, but it's never been detected in any way. That's probably the first big piece of science that will come out of the LHC if the Tevatron at Fermilab doesn't beat them to it. But then also, that's great for the LHC, but they're also going to be looking directly for other new particles. That's what particle physicists do, is they look for new particles that will extend the standard model. They'll look for these so-called supersymmetric particles. Supersymmetry is a theory that is supposed to help extend the standard model. It's just an idea. Again, there's not been any direct evidence for any of these particles, but it may be that the LHC is the first accelerator to detect them. And some of the experiments that I'm involved in, we're trying to do some of the same things. We're not trying to actually observe new particles directly, but by doing some precise measurements, what we want to do is, observe little deviations from what we expect, and from that, learn things about, hopefully, things like these new supersymmetric particles and things of that nature. So I think the nuclear physics and particle physics community are trying to hold up their end of the deal to explain what's going on with the things that the astronomers are observing.
Mark, do you know when the telescope in Chile will be online, or when it's expected to be up and going?
The best estimate is probably 5 to 7 years from now.